and welcome to episode 4 of CS350 Online. I'm your host, Leslie, and on today's episode, we're going to do a brief review of threads, and then we're going to start into a new topic on synchronization. But before we get started with that, let's look at our OS of the day. So our OS of the day is called MCP for Master Control Program, and this operating system was released first in 1961, and it's a product of the Burroughs Corporation, which has long since been bought out by other companies. Now, this particular operating system was released for the Burroughs small, medium, and large systems, and is actually kind of still around in a weird way, but under a different name of Unisys ClearPath MCP. And in fact, I believe there's even a web emulator that you can play with to actually try this operating system out, if you were curious. All right, now this operating system is actually one that's quite notable because it was the first operating system to be written entirely in a high-level language. And what we mean by that is previous operating systems to this one were actually written in pretty much pure assembly or binary. And that would have been a pain in the butt. And I'm sure you remember from 241 having to write little programs in assembly. Now imagine writing the whole operating system in assembly. That wouldn't be very fun. So MCP was actually written in a language called SBAL, which is the Burroughs variation / extension to a programming language known as ALGOL. So it included, some extra macros, some syntactic differences, and so on. All right, now some other important things is that MCP was one of the first operating systems to support multiple processors. So it actually had multi-threading, but not context switched based. So it could do multiple threads at the same time, but just on different CPUs. It's also the first commercially released operating system to implement virtual memory, which is a pretty big topic in this course. Now, it also offered a large number of other things that we use today or have evolved from MCP into operating systems that we use today. So, journaled file systems, guess what? Burroughs MCP was one of the first operating systems to do that. They also had high-level job control, discussion of ports. And one of the most interesting things about MCP was that in order to use the MCP operating system, you actually had to purchase the Burroughs hardware, which meant you had to spend millions of dollars to buy this room-sized computer. And so Burroughs thought to themselves, well, you had to buy our hardware in the first place, and the only operating system you can realistically run to make use of that hardware is our own. So you know what? We're just going to give you the source code to the operating system. And what's interesting about this is kind of the beginnings of something that looks like how the open source movement actually works. So since all of the Burroughs users actually had the source code to MCP, they could find bugs and add features, and then they actually started sharing their patches and their little add-ons with each other. So they created this little community of sharing patches and so on. So that's kind of a neat thing about it. All right. So what did we do in our last episode? Well, in our last episode, we were discussing threads. And in particular, when we were discussing threads, we were looking at how do you take multiple threads and have them actually appear to run at the same time. Because we know how to make threads run at the same time, you just throw hardware at the problem. But how do you, when you don't have enough hardware to support threads running in parallel, how do you make the user believe those threads are running at the same time? And the answer was to do time sharing. That is, we're going to rapidly switch between our threads every, 30 or 40 milliseconds. So a whole bunch of threads are getting an opportunity to make progress per second. And that kind of gives us the illusion that everything's running at the same time. Now, of course, the problem is threads don't want to be interrupted. They don't want to stop executing so somebody else can go. So what we have to do is preempt a running thread, that is, force it to stop. The tricky thing there is that if the operating system needs to stop a thread, but in order to do that, the operating system would need to run some code, but the thread is running, then the operating system would have no way of stopping that thread. So in order to stop the thread, what we're actually going to do is use the clock device. And the clock device is going to throw an interrupt every so many milliseconds. The interrupt causes that trap frame behavior, which is going to cause us to pause execution of the current thread and then immediately execute the interrupt handler, which will discover that the scheduling quantum has expired, and therefore we actually need to preempt the thread and call yield on behalf of that thread. So that's how we implement that preemptive concurrency, where we're forcing threads to give up the CPU. All right. Now, before we get into our new topic, I introduced a sample problem to you in our last episode. For those of you who have access to Piazza, and if you don't, please do let us know. This is 2 threads we are looking at. So let's take a look at it. So we've got this little snippet of code that says from I equals 1 to n, we're going to do c milliseconds of computation followed by s milliseconds of sleep. And what we want to do is figure out at what time do the 2 threads actually complete. And to make the problem a little more interesting, we've introduced a scheduling quantum and some relationships between the compute time, the sleep time, and the scheduling quantum. So let's take a look at this one. So for the first one, we've got C is less than S, and we've got C is less than Q. What that's saying is that our scheduling quantum is much bigger than the length of our computation time. So actually what's interesting about this particular problem is the scheduling quantum doesn't come into play. When we are sleeping, the scheduling quantum is irrelevant, because if you were sleeping, you are blocked, therefore you are not running anything on the CPU, and therefore we don't care. So since Q is bigger than the computation time, we're never going to get preempted, so we can completely ignore Q for this problem. All right, so how do we go about solving this? I actually recommend that you draw it out. And what I typically like to do is, just to make it very clear as to the difference in the lengths, I like to represent C and S by some number of X's and Y's, or C's and S's. So we're going to say C is going to be equal to 2 X's here, and we're going to say S is equal to 3 Y's here. So then we always start with thread 0. So let's do thread 0 goes first. Now while thread 0 is executing, thread 1 is not doing anything because it hasn't even started yet. And it's only when thread 0 goes into its sleep cycle that thread 1 actually gets to start up. Now what's interesting here is you see that since the compute time is actually less than the sleep time, the 2 threads will actually be sleeping for some small amount of time that overlaps. I'm just going to draw this out for a little bit. I'm going to try to keep the X's and Y's lined up. That's a little easier said than done. This is the last, this is the nth here. And since T1 started at an offset of C, you're going to see that it's actually going to end at an offset as well. All right, so there's our computation. Now we have to figure out how long does this take in total. Well, what I'm going to do here is I'm going to observe that there was a repeating pattern here. You can see it like this. There's my repeating pattern. Just like that. Now, the other thing I observe is that it's almost as if thread 1 doesn't exist, because what you've got is T0, and it ends here after repeating n times, and then there's just a little bit extra of T1 that happens after T0 has done its n blocks of this little for loop. So what I end up with to compute the length of time that this takes to complete is n c plus s. So that's going to be how long it takes for T0 to complete. And then I just need to figure out what is the length of this extra bit at the end where T1 is just finishing off its sleep. And we note that T1's offset was equal to C, so that's going to be equal to C as well, because we have no extra weights or anything in play there. So this ends up being n C plus S plus C is what you should get for the first one. That's not too bad, right? Okay, so let's look at part B here. Let me scroll, or maybe it won't let me scroll. So let's just adjust the size. There's B. So in part B, we have a slightly different arrangement. And in this case, we actually have the quantum is still bigger than the compute time, but now we have the sleep time is less than the compute time. So S is less than C is less than Q. So what I'm going to do here is I'm going to say S is equal to 2Ys and C is equal to 3X's. And what you're going to see is that we're going to need some extra wait time. So extra waiting is going to be Z. Like that. Okay. Now we have a question on Twitch here. If there are 2 threads and it repeats n times, shouldn't it be n over 2 time? No, because we are... each of the threads, we want to know at what point in human time are both threads actually done. And since the threads have to do the C plus S, you get NC plus S for the first thread to finish. And since the way that the sleep and the computes worked for the previous one, what you're going to end up with is they almost overlap exactly. And we're not going to add the time of T0 to T1. We're just going to say, okay, well, T1, it took NC plus S, and then due to how the compute and sleep cycles overlapped, there's just a little bit of leftover T1, and that leftover T1 is equal to C. Now, this one is different. All right. So in this one, again, we're always going to start with T0. And we're going to do its compute time first. And then its sleep time. And when T0 goes to sleep, that's when we're going to run T1. Now what you'll notice is that T1's compute time is 3 units, but T0 is done sleeping after 2. Some people might think that T0 should then get to run immediately when it's done its sleep, but that's not what's going to happen here. We are only going to get preempted if our quantum expires. And our quantum's not going to expire here because it's bigger than our compute time. So what ends up happening is T0 ends up performing an extra wait. It has to wait for T1 to actually finish its compute time before and go to sleep before T1 can run or T0 can run again. So we're going to do this extra waiting here. And that pattern is going to repeat. There we go. All right. So now we need to look for the repeating pattern here. And what we're seeing here is that we are alternating between T0 doing its computation and T1 doing its computation. Now, what we see is that the length of each of these segments is equal to C. This is equal to C. This is equal to C, and this is equal to C. But of these lengths of time that are equal to C, one of the things that I observe is that only half of them are for T0 because they're taking turns. T0 goes, then T1, then T0, then T1. So what I'm seeing is that there are actually 2n of these compute blocks because T0 has to do n compute blocks and T1 has to do n compute blocks. So we're going to end up here with 2nc. And then we need to figure out, well, what's left over? Well, what's left over is just the sleep time for thread 1. So we end up with 2nc plus s. And there you go. Now we know at what time both of the threads are actually done. And that's all there is to it. Now, if you're looking to try to get a bit better of an understanding about what's going on here, some recommendations that I have would be to actually try to do this with some different values. So why don't you try it with, so if you're wondering why you keep seeing me close OneNote and then open it back up again, it's because there's a bug in it on Mac, and I'm not really sure why there's a bug that bad. So what you should try is try an example where C is equal to 2Q. That's a fun one to do. And let's say C is less than S or something like that. So there's one example. So example A you can try, and example B you can try. Try C equal to 2Q, and let's try C greater than S. So those are two problems that you can try on your own at home, and if you come up with a solution, by all means, please post it to Piazza, and one of the instructors, one of us, will let you know whether you're on the right track or not. All right. So that then is the end of threads, and I would like to start our new topic now. And our new topic, if you're following along with our course notes, is synchronization. So here's the thing. We have given you threads in concurrency, which is going to improve your CPU and resource utilization. It's going to potentially improve your performance. It's going to help you phrase your code better when you've got a pretty complicated piece of code. We've given you this powerful tool. But with many powerful tools, there's dangers. If I give you a chainsaw, it's a powerful tool, but it's also a very dangerous powerful tool. Very dangerous powerful tool. So, what's the danger of having threads? Well, you know what? Let's run a little sample program. So, I've got my laptop back updated here. I know I tried to show you a little bit of a demo the other day of OpenMP, and it didn't work. The reason was a Mac update took out my OMP library, but I've got it all fixed now. And I have this little piece of code, and it doesn't do much. We have two shared variables. We have total, which is 0, and that's a global variable. And I have n, which is equal to 1,000,000. And then I have an add function, which is going to add total, or increment total by 1 1,000,000 times. And then I have sub, which is going to decrement total 1,000,000 times. And then what I'm going to do is I've actually created two specific threads here using OMP. So you see here this preprocessor directive, pragma OMP parallel, and I've specifically created two threads. The first thread is going to call add, which increments total by 1 a million times, and the second thread is going to call sub, which is going to decrement total by 1 a million times. And then when those two threads are done, what I ask is to actually print the value out. Seems pretty straightforward, right? Okay, so what happens when I run this little piece of code? Now, before I actually hit go on this, the question is, what do you expect the output to be? Now, we know what the output should be. The output of this should be, if I increment the total 1 million times and I decrement it by 1 million times, the final answer should be 0. And that's the truth. The final answer of this little program should be 0. But what is it actually? That's not 0. That's 276,821. We better run this again. Oh. 458,426. Still is not what I'm looking for. Negative 565,343? What's going on here? Well, what's going on here is the dangers of concurrency and multi-threading. What's actually true is I could run this program 2 million times and I can get a completely different answer every single time. And in fact, the number of different possible outputs is 2n. It's huge. There are 2 million possible outputs here. And from this basic C code, it's probably very hard to see why that is the case, but it is the case. So let's take a closer look then to see why this is happening. All right. So what's actually going on here is the fact that all of our threads actually have shared access to some parts of the address space. So all of the threads of a process are sharing the code segment, the globals, and the heap. And what happens is you have two threads, and those two threads are trying to access the same shared piece of memory at the same time, or approximately at the same time. And when they do that, you can get some funny behavior happen. And we call that part of the program, by the way, any region of the code where you have multiple threads potentially reading or writing from a shared region, we call that a critical section, because how the threads are going to behave in there could be very critical. So here is, again, the sample code that we just ran. This is just using C. I want you to ignore this word volatile for now. We are going to come back and talk about volatile another day, but not today. And what you'll see is here's my two blocks of code. I've got the add code, which is going to increment total by 1 n times, and the subtract code is going to decrement total by 1 n times. So here's the problem. If you're doing concurrency, and we are doing concurrency here, context switches can happen at any time. We actually have no control over that whatsoever. Now you might be thinking, well, I didn't call yield, I didn't block, and I didn't exit. That's true. You didn't do any of those things here. But the thing that you can't control is the preemption. So you can't control the involuntary calls to thread yield because you've exceeded your scheduling quantum. So what happens if you're in the middle of incrementing total and there's a context switch? Now you might be thinking nothing happens because this is a single line of code and we're going to increment total and it's just done. End of discussion. Except this is C, and unfortunately, many lines of C code do not translate to a single line of assembly code. And this total plus plus is one such line. So if we expand that into the assembly, what we're going to see here is that our total plus plus actually expanded into 4 different lines of assembly. The first line of assembly, we have to actually load the value of total from memory into a register, and we're going to select register R8 here. And then, that's not the value of total, that's the address of total gets loaded into register R8. And then I get to load the value at that address into register R9. And then after I've added the value of total into a register, I can increment it. So I add 1 to R9. And then finally, I'm going to store the new value back at the address of total. So that's a lot of instructions here. And for subtract, you can see it's the same thing. And you'll also note that the registers we use for subtract are different. It's because the compiler is not aware that these 2 threads could be running at the same time, and it's just randomly selecting whatever registers it has available at that point in time. It's not going to matter. So here's what can happen. The context switch, the preemption, the timer interrupt can go off anywhere. It could go off after this. It could go off after the for loop line. It could go off after the load. It could go off after the add. It could go off after the store. And depending on where that context switch actually occurs, what happens with this code will change. So let's actually see those different changes. So this one is actually very straightforward. This example here, nothing bad happens. We load the address of total, we load the value of total, we increment total by 1, and we store it back into the address before our interrupt goes off. And then the interrupt goes off, and then thread 2 runs, and it performs its subtraction by 1. And at the end of the execution, total is 0, which is exactly what we want it to be. But this is making the assumption that the interrupt is going to happen after the add has completed or after the subtract has completed. And we have absolutely no control over that whatsoever. Because this is what could happen. We could have the interrupt happen immediately after adding 1 to the value in register 9, which is going to be the current, where total's current value actually is. But of course, thread 2 is completely unaware that the current value of total is stored in register 9. And so it loads into register 11 the value of total, which it believes to be 0, and then it decrements it and stores it back. And then once we context switch back to thread 1, we end up overwriting all of the work that thread 2 did because we weren't even aware of it. So in this little order of execution, what we end up happening is it's almost as if thread 2 didn't even run. So a question on Twitch is, how long is the scheduling quantum for this add subprogram? I didn't think we'd get preempted enough times to get an answer so wrong. So I don't actually know what the scheduling quantum is on macOS. I'm going to guess and say that 40 milliseconds is a pretty good guess. It could be a little less than that. You should be able to do the add or subtract in that time. But, and here's the big but, during that scheduling quantum, your code may not be the only code that actually runs. There are a number of, so if there are interrupts, we'll be disabling other interrupts from happening, but we typically don't disable interrupts. That is, we don't turn off preemption if it's an exception and there may be many memory or other normal exceptions like system calls happening while I'm executing this code that may impact how often this issue actually happens in our code. So the other thing is, and I mean, if you want to know, by the way, how much time during the execution of your program is actually being used to run kernel code as opposed to your code, when you run time, what you can see here is that in human time, this took 0.012 seconds. But during that amount of time, my system, my kernel, actually did 0.002 seconds of work. And that 0.002 seconds of work may have actually impacted when those context switches occur. Now, there's another problem that's going on here, which someone on Twitch has actually alluded to, and that is the fact that I created 2 threads on 2 separate cores, which is going to make the problem worse. And I will demonstrate what I mean by that in just a moment here. So this is one example of how we get the wrong answer. Here's another example which actually pertains to the code as I just ran it. Let's suppose you have the 2 threads and the 2 threads get run on different cores, which is exactly what was happening when I run it on my machine. So the 2 threads start executing at the same time. And because they are not aware of each other, and they are not aware of each other, thread 1 is going to load the current value of total into register 8. Simultaneously, thread 2 loads the current value of total into register 10. So they both start out thinking that total is 0. And then what ends up happening is thread 1 and thread 2, both to what they believe total is right now, one of them adds 1 and one of them subtracts 1. So up to this line here, thread 1 thinks total is going to have the value of 1, and thread 2 thinks total is going to have the value of -1, which we know doesn't make any sense. And then what ends up happening is when we go to store the updated values of total back in memory, what's interesting is your memory controller can actually only do 1 write to memory at a time, so they actually go sequentially. And if thread 1 ends up doing its write first, then that write will get clobbered by thread 2 doing its write. And so what you end up getting is, in this case, the final value would be -1. It's as if thread 1 never ran. In the example I showed you on my machine here, so running in this terminal, this is actually where the bug, what's going on here. These 2 threads are actually running on separate cores, so they are both trying, they both have the wrong value of total to start with. And so they're making random updates. Now, if we were to run this on a single core, it's not to say you wouldn't still get the same erratic behavior. I would, however, anticipate a lot less of this erratic behavior because the program is so simple and there are so few system calls or exceptions going to happen that I don't think the scheduling quantum would cause as many issues here. But running on 2 cores, yeah, it's going to cause a lot of problems. Okay. So this is a very simple example, and let's be honest, this is not code that you run. Nobody writes this program. This is just a stupid little example. And there's a name for the problem that we just had. So what you see here is this here in the notes, we have 3 different traces through this silly, simple program. And each of the traces through this simple program gave us a completely different result. And each time I run this on my shell there, we again get a completely different result. There is a name for this. When your program's output, your program's result, depends on the order of thread execution, we say that your program has a race condition. And there are actually 3 different sources of race conditions. We are going to ignore 2 of them for now, and we will come back to them later. But for now, the source of race condition that I care about is your fault. It's your implementation that caused a problem. Now, I know you have no control over when preemption happens, but there are ways that you can write code such that it doesn't matter. And we have not done that. So what I want to do now is look at some other ways that race conditions can show up. So that was a silly, simple program. The race condition showed up in the form of just wrong output. What I want to do now is I'm going to open OneNote back up and hope it behaves for me. Let's open up a new page. Some lines here. So what we have here on my left is a little bit of code to operate on a linked list. In particular, this is actually going to be removing the front element of a linked list. So very straightforward piece of code, not too complicated. The question is there a race condition in this code? So let's assume that this piece of code is run under a situation where there are multiple threads that are trying to add and remove things from shared lists at the same time. Would we have a race condition? And if you're sitting there trying to hash it out, don't worry, we're going to go through this, but the answer is yes, there is a race condition here. So let's actually look at one of the ways that the race condition can show itself. So I'm going to assume that my list, we'll call it LP, has this is first, and this is going to be our item, and let's say our item is 87. And we're also going to have a pointer to the last item, and since my list contains a singular item, first and last are both pointing to 87, okay, which is our first item. All right, fairly straightforward, right? I think so. Okay, now of course this item is going to have a next, and next is going to point to null here. All right. So now let's have 2 threads. So thread 0 is going to first check, is the list empty? So we do the assert. The assert checks out because the list is not empty. So then we're going to say element is now going to be a pointer to first. So element is going to point here. And then let's suppose that we have a context switch. I'm going to shorten this to CS. And now we're going to have thread 1 run. And I'm going to tell you thread 1 is going to do everything. So it does the assertion. It's going to then have its own element point up here. And then it's going to set num equal to 87, which is the value at the element. And since first equals to last, then it's going to come in here and it's actually going to set, I'm going to draw this in a different color. It's going to set first and last equal to null. And then it's going to decrement the counter, so num in list is now 0. And then it's going to free the element. And we return num. So thread 1 actually gets to execute this, or thread completely. And then there's a context switch back to thread 0. Now remember, on a context switch, because we save the state and then we restore the state, thread 0 is going to continue at the exact place where it left off. And it left off after just setting element equal to LP first. So here's the thing. That element that it was pointing to was freed by the other thread. And then I'm immediately going to set num to equal to LP first item, except LP first is null. So what we're going to end up getting is a segmentation fault. Oops. All right, so here is a race condition where the output isn't the wrong answer. The output is a runtime error. We ended up dereferencing null as a result of the order of thread execution. That's another problem. So race conditions can, so far we've seen them show up in two different ways: wrong values and runtime errors. Are there any other ways they can show up? Indeed, there are. So again, we have another simple piece of code here. This time, this one is not removing things from the list. This is going to append a new item to the list. And for this example, what I'd like to do is I'm going to start my list out by having first, I'm just going to represent them by F and L. I'm going to have both of them point to null, and the count of things in my list, because it's empty, is 0. So I'm starting out with an empty list this time. And now what's going to happen is two threads are going to try to add something to this list at the same time. It's totally possible. Now you might be wondering, why would that ever occur? Okay, well, maybe you're Amazon and maybe there are two list sellers that are trying to add inventory to Amazon's database at the exact same time. What's going to happen? All right, so let's follow this through. We're going to get to T0 to start first. So it's going to create an element. We're going to malloc that. So here it is. I'm not going to connect it up yet. And I'm going to then set the value of the items. So I'm going to set it to be 87 in this case. So there's my element. And I perform my assertion. The assertion checks out because the list is empty. So therefore there are no duplicates in the list. And then I'm going to check if my list is empty. And the answer, of course, is yes, it's empty. And then, so I know that I'm going to enter this branch of the for loop. But before I'm able to execute this instruction here, what ends up happening is a context switch. So what I'm going to get here is my context switch. Like that. And now thread 1, like before, is going to execute this function in its entirety. So it's going to create a new element. And its element, I'm going to create it up here. It's going to be 71. So there's its element. And we make the assertion that it's not in the list, which is true because the list is still technically empty. The list is empty. So what I end up doing is, because the list is empty, I am now going to take the first pointer and point it to my new element, and I'm going to take the last pointer and also point it to my new element that I just created. And then I'm going to increment my counter. So now I have my count is equal to 1. Ta-da! All right. And now we have a context switch. Back. Ooh, that's a really bad line. So the question on Twitch is, to be clear, the function T1 is executing some imaginary function outside our slide right now. T0 and T1 are both executing list append at the same time. All right, now we go back to T0. T0 is going to continue from the exact point it left off, and T0 believes that the list is still empty because that's where it left off. So T0 is now going to make the first and last point to its element, which means these pointers are now pointing at this element right here. And then we're going to increment the counter, which now goes up to 2. Here's the problem. There's only one element in the list, and that's 87. But the counter says there's 2. Furthermore, where's element 71? 71 is created, it is on the heap, it is supposed to be a part of the list, except because of what T0 did, where that context switch occur, we now no longer have a pointer to element 71. What we've just created is a memory leak. And this could happen 1,000 times. So you could have 1,000 different threads trying to add an element to an empty list at the exact same time, and 999 of those elements may get lost into the ether. That is, they may be memory leaks. So our list says there's 1,000 items, but there's technically only 1, and 999 of them are lost. So a race condition can present itself as an incorrect output. It can present itself as runtime errors. It can also present itself as things like memory leaks. Race conditions are really bad. And Google actually did a study, I think it was last year, on the Linux kernel. And I think they found something like 300 race conditions and synchronization issues. 300 in a kernel that is everybody uses. That's pretty amazing. Now, I believe that many of those issues are probably stemming from the device drivers, but that's still a lot of issues. Now, I'm not saying that macOS has none, and I'm not saying Windows has none, because I'm sure they have equally as many. It's just the sheer number did actually come as a surprise to me. And the truth is, fixing these race conditions is really, really hard sometimes, as you're going to discover on assignments A2A. And A2B. All right. So you've seen how these race conditions come out. You've seen it in a few different situations. So now the question is, how do we fix it? So another question on Twitch is, so why would the threads all be hypothetically running the same code? Well, you could think of it as, so let's say you are you want to create a list of every Wikipedia article that contains the word Mr. Goose. So you could go through all of those Wikipedia articles one by one, i.e. sequentially, to create that list, but that would be really slow. A much faster way of doing it would be to use like a map operation, where you actually create like 10,000 threads, and each of those 10,000 threads is going to go through a subset of Wikipedia articles. And then each of those 10,000 threads, as they find articles that contain the word Mr. Goose, they would need to be adding that article to the list of articles, which is in the heap. And so it's possible for all 10,000 of those threads to be adding an article to the list at the same time. So it's entirely possible in many different circumstances to have all of those threads, if they're all kind of doing the same task or a related task, that they might all be actually accessing the same piece of memory at the same time. So the next question is, so race conditions are a result of unintentional context switches rather than issues with the logic and the code itself. So the race conditions that you're seeing here, the code itself, like this code to do list append, it's correct unless we have this running in a multi-threaded environment. If this is running with a multi-threaded environment, then this is not correct code, because the context switches, which are involuntary, can cause the race condition, and we need a way to fix that. We can't stop the involuntary context switches, nor do we want to stop the involuntary context switches, so we need to change our code to be able to handle involuntary context switches. All right, so how do we do that exactly? How do we fix our code so that these critical sections, where it's very clear we only want one thread accessing this at a time. It's not so much one thread accessing this region of code. We only want one thread accessing this list at a time. So the race condition happens when we have multiple threads reading and writing the same piece of memory at the same time. It just so happens that if two threads are trying to execute this piece of code on the same list at the same time, we end up with a problem. How do we fix this critical section here? Well, not everything is going to result in a race condition. For one, if every thread is only going to read the variable, if there's no threads that will write to the variable, then there's actually no race condition, because reads aren't going to cause updates to be lost, or when we read from memory, we're not going to get the wrong value, because we're never changing the value. So if everybody's only reading, there's no problem. The problem comes when you have writes, because writes require a read, or any combination of reads and writes together. That's going to be where your race condition comes in. Okay, so what are we going to do about it? We've got to modify our code some way such that if there is an involuntary context switch, it doesn't pose a problem. What are we going to do? Okay, let's for a moment think about what we're actually asking. What we're asking is for a region of memory, i.e. the list, or the shared variable total, I want mutual exclusion on it. I want only one thread to be able to modify that variable at any time. Makes sense. Another way to think about this is if you are, let's suppose, if you are you're a student at the school, and let's suppose you were actually physically at the school, which I know we are not, but you go to the DC washroom and you want to use it. Presumably, you want mutual exclusion on the bathroom stall. I mean, I'm saying presumably because maybe you don't, but let's suppose that you do want a mutual exclusion. You want to be the only person in that bathroom stall. How do we guarantee that you have mutual exclusion on the bathroom? Well, there's a locking door on the bathroom, so that when you show up to the DC washroom and you see the door is open, hey, I can go inside. And the second you go inside, you shut the door and you lock it, and that prevents other people from coming inside. And when you are done, you unlock the door to let the next person in. And likewise, if you show up to use the washroom and the stall door is shut, you're going to have to wait. You can't just like push the door open and go inside. I mean, technically you could, but you get what I'm saying here. So what we want to do is for these areas that are critical sections where we want mutual exclusion, we actually want to add a locking door mechanism. We're going to call it a lock. So how do we create this? So this is our first implementation of a lock. So we're going to set, again, please ignore this word volatile. We will come back to volatile later. So we've got total, which is our shared variable. And I want to create a lock. So maybe my lock could be something as simple as a Boolean that indicates whether the door is open or shut. So if the Boolean is false, it means the door is open. And if the Boolean is true, it means the door is locked. That seems very straightforward. And then what's going to happen is before I try to change the value total, before I go into the washroom, I have to check and see, is the door, can I go in? So I'm going to have this acquire function. And inside the acquire function, it's going to check to see if if I can get in. And if I can get into the washroom, then I will be able to enter the critical section and increment total. And then I'm going to need to release when I am done incrementing total. So I check the door to the washroom, I drink my bottle of water, and then I leave the washroom. I really don't know why people need to drink their water bottles in private. Whatever. All right. And then what I have to do in order to make sure this works, so this is not enough. It's not enough just to have an add total protected by this locking mechanism. Everywhere that uses total has to be protected using the same lock. Otherwise, we're not giving mutual exclusion. I mean, it doesn't make sense for each person to have their own door to the DC bathroom stall. Because you could go in your door, and sure, your door has mutual exclusion, but somebody else could go in their door, and now you awkwardly stare at each other. All right. So, how do we implement this acquire and release function? That's where the interesting stuff comes. And to the person on Twitch who has asked, can't there be a race condition when accessing total lock itself? We're getting there. I'll answer that in a minute. Okay, so what I want to happen is inside of acquire, I want to check to see if the lock is available. If the lock's not available, I want to wait. So this is a really horrible way of doing that because it's going to spin. So this is, you show up to the washroom and it's in use, and so you're going to, you check, oh, the door's locked. And then you're going to sit there knocking on the door. Hey, are you done yet? Are you done yet? Are you done yet? Are you done yet? Until the person is done. So we're going to check in a loop for when the lock is equal to true. If the lock is not equal to true, we will stop looping, which means the door is open and we can now take the lock. So while the lock is true, spin away. And keep on spinning. Once the lock is false, it means we can now enter. And so we are going to then set the lock to true, and then we can finally return from acquire and enter that critical section. And then all release does is just set the lock to false. So the question here is, does this work? No, it doesn't work. This does not work at all, because there's a race condition in our implementation of the lock. And if we're having a hard time seeing where that race condition is, we don't even have to go to the assembly here. So here's the problem. Let's suppose there are two people, and let's suppose that you show up to the DC washroom at the exact same time, and you both see that the door is open. That is, the lock is available. The lock is equal to false. So you both see this at the same time. So person one sees it, and so they exit the waiting loop, and then before they're able to take the lock, they have a context switch over to the other person who sees that the door is open, enters the washroom, and shuts the door, or tries to shut the door. And then context switch back over to you, because you don't recheck at the end of the context switch, you still believe the lock to be available. So you take the lock and enter the critical section as well. And now we have two people staring awkwardly at each other inside of a washroom stall. So what ends up happening is, because there can be a context switch between testing the lock's availability and setting the lock to be taken, we can actually end up with 1,000 people in a single washroom stall staring at each other. So it doesn't work. Well, what are we going to do to fix this? Now, if anyone out there has been doing any kind of concurrency studies on your own, or maybe you've for some reason taken 343 first, you know that there is technically a way that we can do this in C. You can then use things like Dijkstra's algorithm or Peterson's algorithm to actually create a lock, a mutual exclusion on a critical section. However, those algorithms, I want to say, are not fast enough. They are actually a bit slow, and they are rather restricted, and we are a kernel of an operating system. We need these things to be super fast, super efficient, and we also need them to be able to work with any number of threads, which those algorithms that I just pointed out, there's at least one problem with all of them. So how are we actually going to make this work? And the answer is, to make this work efficiently, and generally, we can't really do this with just C. We're going to actually need our hardware to help us out here. What we need is an atomic test and set operation. So I need to be able to test whether the lock is available and set it without being interrupted. And since I can't really do that in C efficiently, I need my hardware to provide an atomic test and set for me. Okay. Most modern architectures, since the dawn of concurrency, have been doing this. And in x86 or x64, so that's the Intel-based architecture, not a RISC-based architecture, they offer one such instruction called exchange. Now, exchange, if we were to look at the logic of exchange, we are getting the old value at an address, setting the value at the address to be something new, and then returning the old one. It's a swap. Except this swap is atomic. So this is the logic of the exchange instruction. But here's the difference. If this was C code, we could be interrupted anywhere here. But because this is an atomic assembly instruction, it cannot be interrupted. Can't be interrupted. So this atomic operation can't be interrupted. Now, can't be interrupted is a tricky concept because we also have atomic C functions. An atomic C function is just, even if it is interrupted, its behavior is unaffected by the interruption. So we're using atomic to either mean it is not possible to interrupt this, or if it is interrupted, the behavior does not change. So it has no impact. So exchange is one instruction we could use. And then what we're going to do is, in our lock acquire function, we're actually going to use inline assembly instructions to make use of that atomic test and set. So our acquire function now is a single line while we are exchanging the value of the lock for true. While that returns true, keep spinning. And when that produces false, we'll stop spinning, and we know we own the lock. Now, why does that work? We want the lock. We want to take the lock. So we want the lock to be false. So if the lock is true, we exchange true for true and we keep spinning. If the lock is false, we set the lock to true and we return the old value, which is false, which means we take the lock and we stop spinning at the same time. And then release doesn't change. So exchange gives us one method for doing an atomic test and set and implementing our lock. And this works. For those of you who are thinking this is how you call assembly and functions in C, this is not. This is pseudocode. Inline assembly is not that pretty. I will show it to you later. We do not expect that you do any inline assembly for this course whatsoever. I don't even expect that you know how to do it. It's hideous. Okay. Now, what are some other ways that this can be done? Now, normally this is where I would show you how Spark does it. Spark does it quite similar to x86, except its instruction is called compare and swap. So if the value of the lock is what we expect it to be, then we swap it, and if it's not, we don't. Okay, well, we took Spark out. And the reason why we took the Spark architecture out is because nobody knows what that is anymore, sadly. For those of you who've never heard of Spark, Spark was Sun Microsystems, which is a dead company, their architecture, and it was the first 64-bit CPU to market. So it's pretty cool. It was also a RISC CPU, which is kind of nice. All right. So I've decided to replace our discussion of Spark with ARM because many of you, of course, have either seen ARM in CS350 or you've heard of ARM otherwise. Now, how ARM does it is actually pretty much identical to how MIPS, our own architecture, does it. And in fact, ARM and MIPS are actually incredibly similar to each other in their instructions. But let's talk about ARM for a moment. So ARM, instead of using a single instruction to do an atomic test and set operation, what they have is a pair of instructions that behave as a barrier. So they have something called exclusive load and exclusive store. And they have to be used together in order for this to work. So the idea is the exclusive load is going to check the value at an address. It's going to keep track. Okay, the value at the address right now is this. And then it calls the exclusive store operation. And what that's going to do is before we store, we're going to check the value at that address again. And if the value at the address between the load exclusive and the store exclusive is the same, then I know that nobody has touched this thing. And so it is safe for me to store a new value there. So we're going to recheck the value. If it hasn't changed, we're going to set our thing. If, however, this exclusive store operation sees that the value at that location has changed between the load and the store, then it's going to fail. Now, these two instructions, as I said, they make a barrier and they don't work on their own. Because if the store fails, then in order for us to do the atomic test and set, we're going to have to try again, which means we're going to need a function in C to force the try again until the store exclusive actually succeeds and actually takes the lock. Now, you'll notice I made the distinction between succeeding and taking the lock. It's because these instructions are not designed for just doing locks. They are designed for atomically setting the value at an address, not just setting it to true and false. So how does the code for this look like? So first we're going to create this little function here called test and set. And what it's going to do, and again, this is pseudocode, this is not actually how you call inline assembly. We are going to set temp to be the value we get from the load exclusive instruction. So this is our initial barrier here. And then we're going to call the store exclusive instruction, and we're going to pass it the value we want to store at the address, and we pass it the address. And we're going to store the result of this operation in results. If result is equal to success, we're going to return the old value of the lock. Now you might be thinking here, but if I succeeded in setting the value of the lock, does that not mean that I now own the lock? Not necessarily. Because if the lock was true, and you're trying to take the lock, so you tried to set the lock to true, and no other threads have played with the lock, then the store exclusive will succeed. But you didn't get the lock. So we have to return the old value of the lock so that we can figure out whether or not we need to keep spinning. If, however, the store exclusive failed, then we're going to return true because we want to keep spinning. Now you might be like, well, if it failed, then by definition the lock value changed. And it would be changing from true to false or false to true. But couldn't I just like take the lock then? And the answer is no, because this is not just going between true and false. This could be changing to other integer values. So we never want to make that assumption. This test and set operation will be called in the while loop. So while arm test and set returns true, we're going to keep spinning. The only point in time where this will stop spinning is when the lock was false and we succeeded in changing it to true. It's a little bit tricky. Now, in MIPS does it the same way. There's a pair of instructions that behave as a barrier, but they behave in the exact same way. There's load linked, which is LL, and store conditional, which is SC. And we're going to use them in the exact same way. So if you look at our lock Aquire, you end up having this MIPS test and set, which does the exact same little bit of code as we did with ARM, and we're going to use the test and set in the same way in our while loop. Now, you might be wondering, well, doesn't this mean there's going to be a lot of looping, a lot of checks? Yes, there's going to be a lot of extra, well, there may be a few extra loops here. There is a recommendation within the ARM specification that says that the open barrier and the closed barrier instructions should be within something like 128 bytes of each other, because you want to give it the best possible chance of succeeding. Because if you're not going to give it a good chance of succeeding, let's say your LL is up here and your SC is way down here in your code, then the chances that there is something happening in here are going to increase. So they're recommending that you put them really close together. All right. So that is how we're going to implement our Aquire function for our first implementation of a lock. And I'm actually going to leave this here today. This last bit with these barrier style instructions, I want you to think about that over the weekend, and we will revisit this in our next episode. We'll look at it in a couple different ways so you can see exactly how this behavior ends up giving us our lock implementation. So in our next episode, we will continue discussion of our implementation of lock. We will do A1 question 1 in our next episode together. And why are we giving you pretty much the answer to the first problem on the first assignment? Because if you don't get it right, we're not going to give you 100% of it, but we're going to give you enough that I don't think I've ever seen anybody not get 100% on that part. We're going to do this because if you don't get it right, none of your assignments the rest of the term will work. You have to get locks working properly. So we'll continue our discussion of how to implement different kinds of locks. We will, as part of that, we'll be going over A1 question 1. And then if we have time, we'll also start discussing things like semaphores and condition variables. So we will see you next week.
Can you see it? A social revolution is sweeping the world. Fueled by pervasive internet access, it has just begun. Today, over 1 billion people are on the network. Millions more join every week. As everyone participates, everything changes. Social networks and communities form, and the demand for network services explodes. The question is, how do you use this change to your advantage? How do you rethink your business and leverage the power of the network to build communities? At Sun, we believe the network is the computer. And for 25 years, that vision has inspired us to build the open computing infrastructures that power businesses and communities around the world. Innovation is in our blood. It's how we deliver breakthrough systems that drive the bottom line without harming the environment. It's why we create secure open software platforms and then share them with communities, because it fuels opportunity. We believe the greatest achievements are created by the power of what we do together. That's why we work to expand the network's reach to everyone, because when more people participate, everyone wins. We help the world's great companies achieve the impossible, and we can do it for you. Sun Technologies and Sun People make it possible. Join us and build the future you see.